here today on observatory night, and you're going to visit observatory that's designed to look at mysterious objects floating around somewhere there in space. But I'm here to tell you that right beneath us, inside the Earth, is just as mysterious. So I'll talk about these ghostly particles that can help us map and understand the mysterious depths of the Earth. And I'll also talk about the different type of observatory from what you see today that can help us look inside the Earth. So let's start from different processes that we can observe on the Earth, such as geysers, volcanoes, hot springs, and quite horrific earthquakes. And what do we know about these processes? Why do they happen? Where does the energy that drives these processes come from? What do geologists know? What don't they know? And how can particle physics help to answer the unknown? So let's move on to what we do know. So just very basically, we know that basic layers of the Earth, core, that's the inner core, outer core, mantle, and very thin layer of the crust, as well as we have models of the formation of the Earth, where we can imagine as a lot of rocks coming and smashing together with a lot of energy, which also melts those rocks. And then this whole crater of melted rock starts cooling down, and starts creating these layers that we see right now of the Earth. And then we do know a little bit more about the nearby crust areas of the Earth. So we know layers because we can actually measure them, we can take the samples of them, and we know that there's a lot of heat and energy coming from underground. We know that it's really hot down there. We know that there's things moving. There's continents moving around. So there's all these layers with a lot of energy and a lot of heat moving around, bubbling, creating these volcanoes and these earthquakes. But then do we really know where that energy comes from? So how do we know about these things? So these are all the geology methods of looking at the Earth. There is more, but these are the ones I'm familiar with. I'm not a geologist. We look at the Earth with seismology, which looks at the seismic waves traveling through the Earth, and that's how we can figure out different layers and different densities and masses deep beneath us. Then there's geochemistry, and that's actually my geologist friend, Virginia. She took me and a few other physicists onto a geological trip and showed us how they work. I must say it's pretty hard to go in this was in Italy, and it was really hot, and she was smashing those rocks, and I was just sweating looking at her. And yeah, it's a really hard job to take samples, and then they, of course, look at them and count the composition of them and put them through various tests to see what type of metals or what type of elements there is and how they react under different conditions. And then there's also a really cool method that involves gravity, which involves these satellites that are very, very sensitive to gravity flying around the Earth, and seeing how gravity sometimes pulls a little bit harder on the satellite and changes its trajectory. And that way you can map this more massive, denser regions inside the Earth with gravity as well, which I only found out about not that long ago, which is, I think is really cool. So we measure the total surface heat flux, and what that means, we know how much heat we can see coming from the Earth on the surface of the Earth. We cannot really dig deep and measure what's inside there, but we know the total heat that we can see on the surface. And that measured surface heat flux of the Earth is 47 plus minus 3 terawatts. And just to put this in perspective of what this number means, a whole year of human consumption and energy is about 15 to 18 terawatts. And then sun hits us with about 174,000 terawatts instantaneously to the surface of the Earth. So it's quite large number comparison to what we use, but then comparing to how powerful the sun is, it doesn't look that big. So there's two scales that you can look at that number with. So then from all of those processes that I talked here, there's different modeling of where this heat comes from. So from the cooling down of that formation of the Earth, as I said, as the Earth formed, it was really hot and it's cooling down, making all these layers. So we still think that there's some cooling of the Earth that's involved in this heat. And then some of the other processes coming from the core. The ones I'm interested in is the radiogenic heat process, which radiogenic means the heat that comes from radioactive elements decaying inside the Earth's crust and mantle. So this pie chart represents with R star, that's where the radiogenic heat would be from the crust and the mantle. And as you can see in this pie chart, it has quite large uncertainties. So for the mantle, we have 4 to 27 terawatts. For core, we have 9 to 17. For radiogenic mantle heat, we have 8 to 25 terawatts. So it really shows that we don't really know exactly how much heat comes from which source of the heat that we model. So we know the total, but we don't really know how accurate this pie chart is. So in the end, our radiogenic heat from the radioactive elements can be anywhere between 10 or 30 terawatts. And that's quite a large uncertainty when your total number is 40. So again, we don't really know how much of that heat is that primordial formation of the Earth, leftover heat that's still cooling down, or how much of that is coming from radioactive elements buried deep inside the Earth. So then geologists come with 3 different models and call them low Q, medium Q, and high Q. And that just represents 10, 20, or 30 terawatt Earth. And here in blue, we can see crust, and in red, we can see mantle. So for the crust, the number is the same because we actually understand the crust way better because we can measure it, we can touch it, we can take the samples of it, and we can model it really well. But we cannot really dig deep inside the Earth and see the mantle. So I think I was looking it up, and the deepest hole that was drilled so far was about 12 kilometers, but the crust is anywhere to up to 100 kilometers. So we cannot really even be close to digging as deep to take samples from the mantle, apart from some special cases, which might not be representative of the whole mantle. So also, is there any other heat sources that are in the Earth? We don't really know. So another thing that we don't know, and don't be alarmed by a lot of lines here, we don't know the element distribution in the Earth. We don't know what type of elements we have. We don't know abundances and how many of these elements we have in the Earth. So here, there's a lot of different models from multiple geologists who took samples from meteorites and the rocks in the Earth. And they were trying to compare them and compare the ratios of these elements. And they found that all the ratios are quite nicely agreeable in the line here for these elements that are called refractory elements. What they cannot agree is which one of these is correct line to represent our Earth. So if I would be able to say what is the abundances of, let's say, thorium and uranium inside the Earth, then we could actually see which line is more representative of the Earth and of these meteorites. And then we could say a lot more about all of these elements that are deep inside the Earth. So how can particle physics help answer all of these things that I said we don't really know? I have to start with introducing you to particle physics. As geochemists have their periodic table of elements, in particle physics, we have standard model of elementary particles. And basically what you need to take of this is just that this is all of the particles that make up everything we know. So this is all of the matter particles, and these are all of the forces. But what we really need to know is these neutrino particles, and that's what I'll be talking about. And these neutrino particles have really interesting properties that makes them kind of spooky and kind of ghostly, and that's why I have these ghosts here. And why are neutrinos so spooky? So they're particles that are neutral, hence the word neutrino. So that means they don't really create any electrical properties. So we cannot use any magnets or any type of things to look at them. They're very weakly interacting, and it means that they really do not like to talk with us at all, or doesn't like to interact with any type of other particles for us to see. And it's an interesting fact that about 65 million neutrinos can pass through your, even through your little finger every second, and you won't even feel it. They're passing through you right now, and you won't even feel it because they don't want to interact with you. They don't want to talk with you. They're not very friendly. Another thing we don't know about these particles is their absolute mass. So we have an idea of where about the masses of these particles are, but we don't really know exactly what it is. So that's another thing we're trying to figure out. And then another really spooky thing about neutrinos is that there's three types of them: electron, tau, and muon neutrino. With my detector, I can only see the electron neutrinos. The problem is that as the neutrino travels through space, it decides to change its type, and it oscillates. So that's another really spooky thing about neutrino as well. And I have to mention that for the neutrino oscillations, our dear Arthur MacDonald from Queen's University won a Nobel Prize together with Takaaki Kajita for the discovery and observation of this change in flavor of the neutrino in 2015. So we know they're really spooky. What is the geoneutrino that I'm talking about? So geoneutrino is a neutrino particle that is created from the Earth and created from uranium and thorium decays inside Earth's crust and the mantle. So how is it created? We have this uranium, and it's called beta decay, and it decays into a different particle, in this case lead, and produces an electron and an antineutrino. And in this case, this antineutrino then is called geoneutrino. Then we can actually count these antineutrinos, and knowing by how many of them there is produced through from the certain uranium and thorium isotopes, we can, by counting the number of these neutrinos, we can then calculate how much of these uranium and thorium isotopes we had inside the Earth. And this globe shows the heat map of how many neutrinos from the uranium and thorium we expect to see on the surface. So how do we look for these geoneutrinos? As I've mentioned here, something called beta decay. We look for them using inverse beta decay, so the opposite process, where we have this neutrino coming and hitting some proton. So I did mention that they really don't like to talk about, but once in a while, they would come and say hello. So in those rare cases where this neutrino would hit a proton, the proton would then produce a positron and a neutron, so these two different particles, which then would produce some light. So there would be one blink of light and another blink of light. So to get this light and to observe it, we actually built these really, really large detectors to put as many protons as we can in them for the neutrinos to interact. And then we want some type of material that could really see this light and would be good at transferring that light for us to detect it. So when we look and we build our observatories that can observe these neutrinos, we look for a large volume of these protons. We look for them to have very low radioactive backgrounds, which means we want to really see these neutrinos coming from sources we want to observe and not from surrounding source. So we wouldn't put it in some uranium mine where there's a lot of uranium, because that would just blind our detector. And then the material. And then the last but very important piece to this type of observation is patience. A lot of patience to wait and wait for these neutrinos to interact. And that's me working on a detector and practicing my patience. So let me show you the SNO+ detector, and that's the detector I'm working on. And this detector is located in Sudbury here in Ontario. It's a follow-up experiment that recycled a SNO experiment, and that's the experiment that won the Nobel Prize. It's 2 kilometers underground in an active nickel mine owned by Creighton. It's called Creighton Mine, owned by Vale. And inside we have this large cavity, and that's about 70 meters deep. And this is a 12-meter in diameter acrylic vessel where we put our material called scintillator that is good at transferring light and has a lot of protons inside. And then we put these detectors of light around it, which are called photomultiplier tubes, and to observe the light produced by these particles interacting. It's quite a large undertaking to build such experiments and run them. This is what it would look like inside. So this is a picture of the detector filled with water. And this is the picture. Usually it's really dark inside the detector, but for these pictures, we actually turn on some lights to show you how the inside looks like. So this is the vessel where neutrino would interact, and then one of these or multiple of these bubbles around it would detect few blinks of the light, and then we would do a lot of calculations to see if that was actually the particle we wanted to see. So how do I predict the signal of my geoneutrinos? And I know this might look hard, but let me simplify it for you. So how do I know what my expected number is? I look at the production, so that's the rate of how many neutrinos are produced from uranium or thorium. Then I look at this survival of the neutrinos, which is that oscillation that I talked about of them changing into different particles. So I look how many type of neutrinos actually come to my detector. And then this geological factor, which is the one that has the biggest uncertainty coming from different models of geological measurements, as I showed you before, the seismology, geochemistry, which don't really agree with each other. So what I do, I divide the Earth into these different boxes, and I apply the knowledge we know on each of them, and then we do simulation of a computer simulation to calculate how many of these particles we would see. And then in the end, I produce several numbers saying how many of these particles would come to my detector. And here I have about from 30 to 50 of these a year. And this is the best case scenario. So this is the number for the 100% efficiency perfect detector. And I know that my detector is not really perfect, and we have a lot of different things happening. So realistically, I'll expect about 20 of these particles actually coming and interacting inside of my detector per year. So to actually get a good measurement, we need multiple years of actual data taken to see these neutrinos. So because this geological factor is so unknown, we really want to figure out the geology around the detector really, really well. And for that reason, we had some geologists come to the SNOLAB site and take some samples. So it was two of my friends, Virginia, that you saw at one of the first slides, and Scott, who actually visited SNOLAB. And this is the Canadian rock. So they took some samples, as you can see here, and they counted them, and they made this beautiful profile of what geology looks around the detector. So this is the detector site, SNOLAB. These dots are showing all of the different holes they dug in the ground and took the samples. And then they also took the seismology and gravity data and combined all of that to describe the area. So when I'm trying to say, when I'll measure something and I'll try to say something about the Earth's mantle from my number, I should really make sure I know something, I know the nearby environment really well, so I could make a claim about what's deeper underneath it. So then once they've done that, my job is to run the detector and build the detector. And well, I'm not alone building it, but help build the detector and run it, which is quite fun, but also quite a lot of work and dedication to do. I have a lot of fun doing it. So this is me installing some of these photo detectors. That's also me having fun, and that's me fixing some of these. So there's a lot of tasks that we do building this detector, yeah, it's quite fun. So to conclude, there's still a lot of things that we have to discover about our own planet, I hope that particle physics can help these geologists figure out which model is the correct model to model the Earth. Maybe we'll be able to say something about the abundances of different elements inside of the Earth from these measurements, as well as maybe some of the different planets, because we're comparing all of these with different meteorites that we find on the Earth's surface. And I also really want to thank my SNOLAB collaboration. So these are all the people that work on a detector. And that's me. We do various types of science with a detector, not just geoneutrinos. I'm just a geoneutrino person on the SNOLAB. As well as I would like to acknowledge my geology friends from all around the world. I don't actually have a good picture of them. We have a call every week because, so Beja and Uncle O here, but his name is Andre, they're in Czech Republic, and Huey, she's in China, Hiroko's in Japan, Laura's and Bill are from Maryland, and there's me. I look like I'm sleeping, but I swear I wasn't. So this is a big undertaking to measure these geoneutrinos and to see and to look into our Earth and try and understand more about our own planet. So thank you for listening.
Well, thank you for that fabulous talk, Ingrida. All right, we're going to take a few questions. You can raise your hands if you have a question, and I'll come to you with the mic. Once you have the mic, you say what the question is. Hopefully, Ingrida will answer it, and then we can move on. All right, question number 1.
Do you think that human will ever do something like this on another planet?
No, so the geologists model Earth's rocks by looking at samples of different meteorites or different knowledge they have on different planets that we know about. And we are trying to compare how similar the rock on Earth is to different meteorites. I guess understanding more the composition of the Earth fully would help us say something about possibly those planets, but that's definitely not my area of expertise. I'm just trying to measure the particles. So I think hopefully the geologists and geochemists who work on that would be able to say something. Yeah, sorry.
Hi, I'm a historian, not a physicist, so this is actually about the map. But I noticed, if I understood it correctly, the highest concentration of thorium and uranium beta decay, and it seemed also the map geoneutrino flux was centered in Western China. Does that mean that elemental thorium and uranium are most concentrated in the crust elementally in Western China, or is that from the mantle? I guess I didn't.
So that's where the mountains are,
right.
The Himalayas.
Yeah.
So that's where the crust is the thickest.
Oh.
And therefore it has way more uranium and thorium in it because
Right.
it's thicker and it has more rocky type of composition.
But that doesn't necessarily signify like extractable thorium from like a mining perspective. It's that's just total mass in the crust.
Yeah, that figure was more so the total mass.
Oh, okay.
There is talks about maybe distinguishing mineable
Right.
uranium and thorium deposits deeper underneath crust layers. But that would require way more measurements and be more precise than what we do right now.
All right, so one of the worst things about being an MC is to run around the room because two people across the room have a question. It's the worst thing ever, but okay.
It's a good workout.
Hi there. You mentioned that SNOLAB was very big and expensive, so I'm just wondering, like, how much did it cost to build a lab 2 kilometers underground, and how long was the process to build it?
I mean, I don't know the full costs. I could not really quote that, considering I only joined the lab 4 years ago. It was built decades ago right now, so it started all with the snow detector, and I guess I do know that it was quite a costly undertaking, but what happens with these large detectors that it's not only one country that funds them, it's multiple countries that put their funds together to build these large laboratories. So even for our Snow Plus detector, we have US funding it, we have Portugal funding it, we have UK funding it. So there's multiple countries putting together the funds to find, to know more about the universe. I really cannot quote a number. I don't think I would even know the full number. So I don't know, Ben, do you know the number?
$500 million.
Yeah, something like that. Yeah, I was afraid to quote that. Yeah.
Hey, in your lab, are you spending most of the time repairing and recalibrating equipment rather than doing experiments? Just out of curiosity.
Well, that's part of doing an experiment. I mean, so we spend multiple years actually building and calibrating and filling the detector. So for my measurement, I only need the second phase. So our experiment has 3 phases, and we just finished water phase. And my part of experiments is going to be so-called scintillator phase. And I've been on Snow Plus for 4 years now, and the scintillator phase didn't come yet. So it's a lot of work to actually make it run and make it happen because it's such a large experiment. So you want to, once you already take the data, you want to make sure everything's perfect. So we have a lot of people working on different parts, making sure and double checking and triple checking that it's absolutely perfect. So we're not gonna waste 10 years worth of work for a faulty experiment. So yeah, that's all part of a process.
Neutrinos come from different places, including the sun. So how do you differentiate your neutrinos from the other sources of neutrinos that you might find down there?
Yeah, so my neutrinos are very specific type of neutrino. So my neutrinos as well are antineutrinos. A lot of neutrinos from the sun or atmosphere are neutrinos, so they interact inside the detector a little bit differently. So for antineutrinos, my biggest source of background of other antineutrino is actually reactors. So reactors in your burning of nuclear fuel produce a lot of these antineutrinos. But then we actually look at these decays and we model the, I'm sad I didn't put the spectrum here, but we have different energies. My geoneutrinos lay somewhere around from 1.8 to 3.3 MeV energy, and reactor neutrinos lay more from 2.5 to, let's say, 10 MeV, and they have different spectral shape. So once we count these neutrinos, we work really hard to understand all the other sources and their spectral shapes to then be able to distinguish, and we do different likelihood fits to figure out how much of that total measured neutrinos is what type of neutrino, if that answers your question.
All right, any more questions? Going once, twice? Okay, thank you, Ingrida. Let's thank Ingrida once again.